Karl, welcome to Karl's Corner for December 2025. Thanks for joining us. Please tell us about what you've been working on this month.
Well, this month we were bringing to closure, at least in terms of writing it down in the form of an academic publication, the application of information gain, curiosity, if you like, to the very structure of our world models or our generative models in a technical sense. So that's been brought to closure, which means that now it's the next exciting project, and that is basically going back to some earlier work in continuous state space models, which you could best summarize in terms of complex system modeling. So I'm now revisiting work that was done several years ago in order to try and understand the fundaments of how complex systems emerge and change over time. Technically, those systems that evince something called stochastic chaos. So not only are they chaotic and unpredictable in terms of their sensitivity to initial conditions, but there are also aspects of random fluctuations that have to be accommodated. So immediately you're in the world of trying to predict not the actual state of the world or any particular system of interest, but how probabilistically it will change in the future. And the idea here is very much akin to weather forecasting. If you can get the right generative model or world model of the complex system that you're trying to characterize, then you can now roll out into the future and do forecasting and things like scenario modeling. What would happen if this changed, or what would happen if I did that? But in order to answer that kind of question, you have to understand, basically, specify the form of the dynamics and the probabilistic behavior of these systems. And this has many applications from the point of view of what's called translational neuroscience, which basically taking basic understandings of complex systems such as the brain and translating it into clinical practice. An obvious thing here would be the ability to predict the onset of epilepsy. So if you had some recordings of brain activity, say with some wearable EEG or some implanted electrodes, then you are now asking, is it possible to, given the current state of the dynamics and the activity of this complex system, predict an imminent seizure? And if so, can we intervene to preclude that seizure event or that epileptic discharge? Other examples would be in finance. Can you predict a sudden shift in the market? Can you predict a catastrophic event? In the old days, this would have been subsumed in things like catastrophe theory, trying to predict quick changes in the system of interest in order to take some preemptive action to preclude the ensuing surprise. And I use surprise here because this, of course, is technically the description of a system in terms of the free energy principle, which itself is the physics backstory to active inference and much of the work that certainly colleagues at Versus are currently pursuing. But we're now really going right back to the underlying dynamics. So that's what I'm currently working on. There's some really interesting issues that attend this, because you're really starting, you're trying to identify the nature of these models that are fit for purpose for very, very complicated high-dimensional systems that have this sort of chaotic and stochastic aspect to them, with very little knowledge or constraints about how they will unfold in time. So one has to really go back to the physics of self-organization and ask, what is this kind of thing in and of itself? And the only answer is, well, if this system persists over a over a period of time. So, for example, your brain hopefully will persist for decades and decades and decades. And just by existing over a period of time, we now know that your brain and my brain keep revisiting particular states that they were once in. So we have particular characteristic states of being that characterizes the kind of thing that we are. In your instance, it's your brain. In mine, it's my brain. But just by returning to particular states, you now have it's like a definitive or a stipulated definition of what it is to be you or to be me. And that it has some quite fundamental implications. If you're a physicist, you'd call this a pullback attractor. If you were doing statistical mechanics, you call this a non-equilibrium or far from equilibrium steady state, in contrast to the kind of steady states that you get in 20th century physics for closed systems. The equivalent for an open system is a very itinerant kind of dynamics that keep you within characteristic states. So equipped with that knowledge, how can you then install that into a universal generative model for continuous states? And well, I could wax lyric about how we're doing that. At the moment, it's we're at the stage of just generating the behavior of complex systems that conform to that possess this stochastic chaos, but also possess an attracting set of characteristic states, and then generating data from that, and then seeing if we can recover the underlying model, the parameters of the model, the kinetics, the connectivity, the influences, the causal influences, the cause effect structure that underwrites those data. Because if we can do that, then we can take indicator variables. Physiologically, we can take some measured brain signals, for example. In the context of finance, you can take indicator variables that are abundant and monitor the state of the market and people's confidence in that market. So there's masses of data out there, but making sense of that data is the job of inverting this forward model of how those data were caused. And if you've got the right world model or generative model of those data, then you can take the structure of that model and then roll out into the future. And that's what's going to happen in the next minute if you're trying to predict, say, seizure onset, or what's going to happen over the next month. And if you know what's going to happen probabilistically, then you can take preemptive actions.
And so what you're saying there is, for instance, applied to financial markets, you might be able to predict a stock market crash. Let's say, I don't know, there's a 20% chance of a stock market crash, but if these variables change, we will change our prediction to 30% or 10% in the near future.
Yeah, absolutely. It is exactly the same kind of problem that people in weather forecasting contend with. And there are a number of approaches you can bring to the table to do this. And of course, as you go deeper into the future, your uncertainty accrues, so that you have, if you like, a precise focus or a precise belief about what will happen in the short term. But as you get further and further into the future, that uncertainty increases, so you become less confident about the distant future relative to the short-term future.
And you currently, in weather forecasting, maybe we can look a few weeks out before it becomes very hard. Do you have any sense for things like financial forecasting? Are we going to be able to look days, weeks, months? Do you have any sense of that right now?
I do, but I'm rather naive in this game at the present time. However, just from a first principles account, there's likely to be a separation of temporal scales. So let's take weather forecasting. I think exactly the same thing will apply to fintech or financial modeling. So in terms of local fast changes in the weather, Is it going to rain in Bermondsey in the next 2 hours or so? You can make very, very precise predictions. Is it going to rain next weekend? Well, the predictions become less precise. If you go beyond a few days, then it's highly unlikely you're going to be able to provide a precise or a certain or a very confident prediction of what's going on. So at that time scale of days or hours to days, then the ability to predict the short-term fluctuations in the weather attenuates fairly quickly. However, that's not the same as predicting the climate. So there are aspects of meteorology, the way that the weather is caused, that have these fast fluctuations, but ride on the back of these very slow fluctuations. So if I was a climate change modeler, I would use exactly the same functional form and mathematics, well, not quite exactly the same, but similar kind of technology in order to analyze the evolution of the context in which the weather occurs, which is the climate. And it may well be possible to predict years, decades, centuries in advance at that time scale. Indeed, people do that, hence all the current angst about climate change. And that kind of prediction at a slower time scale is perfectly viable. So you have to ask, well, hang on a second, you just told me I can't predict the weather next weekend, yet I can predict the climate in 2050. Well, the resolution of that apparent paradox is that these slower fluctuations live at a different scale to the faster fluctuations. And that's really interesting, because what that tells you is that should be part of your model. And that's exactly what we're currently working on. That you've got these slower fluctuations that could have catastrophic events. They could have sort of excursions from this attracting set and then pull back very, very quickly. But overall, they fluctuate very, very slowly and then provide a context that then explains or generates fast fluctuations from day to day. So, for example, you may have a latent state in your world model of financial data that fluctuates month by month and could reflect the confidence of the markets, for example. And that will be in the context of many other factors or variables or latent states that influence the confidence in the market overall globally. And then that confidence will now provide a context for how you're going to now change, if you do want to change, if there's a sufficiently small cost of changing your investment strategy given the current performance of the assets that you might want to invest in. So then you'd have to build a sort of a deep generative model, very much in the spirit of deep learning. So the depth here speaks to a hierarchical depth with slower things evolving on a particular time scale, and then contextualizing, providing constraints upon the faster fluctuations at the level below. So if you can get this kind of deep hierarchical dynamical model, state-space model, forward model, generative model, whatever you want to call it, if you can identify its structure and parameters, then you're in a position now of doing both the long-term forecasting and the short-term forecasting, noting that the long-term forecasting won't tell you about this particular asset, but it will tell you about the context in which this particular asset is fluctuating and whether you should invest or whether you should not invest. Does that make sense?
That makes a lot of sense. That's absolutely fascinating. Just one question about other things, non-financial things you've been working on this month. Anything to share there?
We're also in dialogue with colleagues now about the sort of the finer details of how to communicate the work that I mentioned previously about smart structure learning, trying to gather the right kind of data or information which will best enable you to disambiguate between different hypotheses, different structures of these world models. And one particularly interesting issue of not debate, but certain discussion how we should unpack this has emerged. And it all relates to whether you can learn to be curious. It may sound a silly question, but it's important, because if you want to deploy conventional machine learning, say deep reinforcement learning or transformer architectures of the kind that you might find in a large language model, you are committed to learning something. But what are you going to learn? Obviously, in the wider context of active inference, you want to learn how to infer. Now, this may sound a bit stupid, but interestingly, it does relate to the separation of temporal scales that we were talking about before. So there's a fundamental difference between inferring something in the moment. So if we come back to our example with weather forecasting or market forecasting, I need to infer whether it's currently raining or whether there is an hourly fluctuation in this particular asset. And that means I have to assimilate the data at hand to infer the state of the world that was generating those data at this point in time. And that's fundamentally different from learning the parameters that govern the slower fluctuations. So when you learn something, the actual thing you are learning are all the associations, for example, connection strengths or connection weights in a neural network. For you and me, it would be the connections between our different nerve cells or neuronal populations, cast again in terms of connectivity. So the connectivity itself doesn't change very quickly. The connectivity is fixed and mediates all the message passing, the dynamics that allows you to do inference. So there are two things going on in any intelligent network, any network or complex system that has the capacity to infer and learn. There's a fast fluctuations that basically reflect sense making and assimilating data in the moment to infer what is the state of the weather, what is the state of the market at this point in time, what is going on around me, where am I? This depends upon getting the right structure and parameters of your generative model. And those structures and those parameters don't change over this short time scale, but as they change and fluctuate over the longer time scale, it looks as if the system is learning. It's finding contingencies, it's finding the cause effect structure that is installed in the world model or the generative model. So there's a fundamental difference between learning and inference. But in machine learning, this is often suppressed in terms of the way that people think about it. So machine learning does what it says on the tin. It learns. So it doesn't infer. Now, there may be implicit inferences in the way that you, say, classify things, or you project the next token if you're a large language model. But those predictions and classifications and recognitions and indeed image generation all rest upon having learned a fixed set of connection strengths and parameters and structures. So the question now, can you learn to infer, is an important question. The answer is, well, yes, you can. You can learn to infer in the sense that if the way that my content is generated doesn't change over time, I can now install that cause effect structure by learning the right parameters and structure of my generative model, which means that if given some data, I can now infer what caused these particular data, or I can generate data with different sort of contextual variables given this fixed parameterization and structure. However, that depends upon me having learned everything that I can from a large cohort of data, and hence the emphasis on big data and the emphasis on building power stations to store the data in large data warehouses. So that leads to the next question: can you learn to be curious? And of course, that's I framed it like that because it's colloquially or in the vernacular, that that will make sense. Technically, what we're talking about, can you learn to be smart in the way you mine your data? To be smart is to choose those data that are going to have the greatest effect on your uncertainty. They're going to reduce your uncertainties to the greatest extent. Mathematically, that is scored by the expected information gain, the amount of information that is afforded to me in resolving my uncertainty. Now, and that has many different there are many different ways of describing this. Some people call this intrinsic motivation, some people call it intrinsic value, other people talk about it in terms of Bayesian surprise, other people talk about it in terms of salience. There are epistemic value, epistemic motivation, having epistemic affordance. All of these are just descriptions of this underlying fundamental quantity, which is the expected information gain. But crucially, the expected information gain depends upon what I don't know. So if I already know it, if I've already learned it, there is no information gain. But if I haven't already learned it and I don't know it, then there could be lots of information gain. If I looked over there, or I looked at this kind of data, or I selected these data features, then I could learn a lot if I hadn't already learned it. But therein lies a paradox. Because we just said you can learn to infer. So, but that depends upon having learned the structure. So there can be no curiosity, there can be no expected information gain after you've learned it. So now you can't learn to be curious. You can't learn to behave in a way that resolves your uncertainty before you learned. So there's a fundamental aspect to the generalization of the principles of active inference to this kind of smart data mining or this kind of epistemic foraging that resolves your uncertainty about the structure and the parameters of generative models that cannot be emulated or implemented using machine learning. And that's the message that it's a bit of a subtle message, but it's a really important message, because you could waste a lot of time trying to evaluate the expected information gain in a way that you could automatically map from some data to the best thing to do with those data, and then what's called amortize it. So amortization, I think is a German word, which basically means deferring payment, making things reducing the complexity cost. So when you normally install machine learning technology into generative models or world models that you would need to do active inference and learning, that installation is referred to as amortization. It's technically it's a mapping from some data to a belief structure, probability distribution, or sometimes a mapping from one probability distribution to another probability distribution. So, for example, how things change in time. So I've got some probability distribution, some belief, and I'm using belief in the sense of Bayesian belief updating. So this is it's a subpersonal mathematical belief. This is a probability distribution over state of the world now, and I want to now learn the next state of the world, say tomorrow or the next second. And I could amortize that. I could sort of just say, well, given that I've learned that inevitably in every context, this probability distribution will change to this probability distribution. I can parameterize that with a neural network. That would be an example of amortization. And that can be quite effective in many instances. But notice what I said, if it's context insensitive, if it always happens like this. So there's a real problem with this kind of machine learning technology when installed in inference machines, when installed in things that have this capacity to quantify uncertainty. And indeed, there's a whole literature on uncertainty quantification. They are context insensitive. You can only learn it if it doesn't change with the context or change over time. And that means that you have to choose very carefully where you do your amortization. And some people have tried to actually amortize the planning in terms of, can you map between some data to beliefs about the state of the world, generating those data, and then map from the beliefs about the state of the world generating those data to the best thing to do next in terms of the expected information gain. And the fundamental point, which I've been wittering on about for about 5 minutes now, is you can't, because by definition, it's context sensitive, because it depends upon what you don't know. And as soon as you act, you now you change what you know, and therefore you change the context in terms of what it is to be curious. So just, to make that very simple, if you move to a new house, for example, then there's going to be lots of epistemic affordances in terms of getting to know how to live in this particular house, how to control the heating system, for example, how to get to the shops. But after a couple of years, all of these epistemic affordances and offerings of information gain decrease. So the best thing that you do now is just to exploit your knowledge living in your house and turn your attention literally to other things. And I use attention here exactly in the spirit of attention heads in large language models, or attention in psychology, or indeed predictive processing. So that would be one example that you can't learn to be, you couldn't learn how to discover how your household works. You could, after you've spent a year or so there, learn how to exploit and pursue your goals in the because you've become old and wise in your particular eco niche, or your particular system, or your particular household. But to get there, you have to recourse to this more universal approach that's implicit in active inference and learning.
And so the implication here is that machine learning approaches alone will not be able to gain information as efficiently as if they maybe are working with or replaced by active inference.
Absolutely. I mean, and that has been the story in the broader community, in my world, specifically the philosophy or a fundamental observation that underwrites a lot of the direction of travel at Verses, in terms of its aspirations to universal intelligence, and just basically being a good citizen, a good institution, in terms of aiming for a much more efficient and sustainable way of doing things, because if we come back to these sort of fundamental problems with that we've rehearsed many times, and I think we're now talking about the sort of the gross and possibly frightening inefficiency that we're currently witnessing in big tech and current deployment of transformer architectures and related machine learning architectures, to the extent that the energy consumption and consumption at many levels is just completely unsustainable. And the root of that is exactly the inefficiency due to the fact that there is no smart data mining, because there's no technology currently in big tech, in machine learning, that allows you to evaluate the expected information gain and get that uncertainty quantification and context sensitivity personal to this artifact or this model into the game. So the whole point is, if we can bring these natural principles of self-organization into machine learning, it will no longer be machine learning, it'll be machine inference and learning. And what you will get is now a much more efficient, both in terms of sample efficiency, because if you're selecting those data that resolve your uncertainty or have the greatest amount of information gain, you will effectively change your mind, you will update your beliefs much more quickly than sampling data that has very little information in it. So you'll get an order of magnitude increase in the ability to predict the future and to plan in that future over conventional machine learning approaches, and that will manifest as sample efficiency. So, and furthermore, that sample efficiency literally translates into the number of joules you require in order to attain a particular optimal kind of performance, or more philosophically, the right kind of self-evidencing.
Well, Karl, thank you very much. That was fascinating as always.
Thank you.